This is Chapter 10, Part 2, the T distribution. So, it's all about the distribution and the transformation. So let's do a quick review. The beginning of Chapter 10, and in the first lecture on Chapter 10, we talked about the Z transformation. Whoops, the Z transformation. Okay, and the transformation we were using looked like this: sample mean minus hypothesized population mean divided by sigma, so the difference in the numerator divided by the quantity sigma over the square root of n. That was the transformation, and Z's distribution is standard normal. So what are the assumptions here? To do a z-test, we need to either know that x is normally distributed, and sigma is known. Sigma is known, given. Somehow we know sigma. And what else? So x is either normally distributed or n is greater than or equal to 30. So there's a sample size requirement. But for both of these situations, there's a requirement that that we know sigma. And this assumption is really unrealistic. So what do? Well, we're going to use the T transformation instead, which is really an honest transformation for the situation, because if you think about it, we will know. We're going to collect data, okay? So since we're collecting data, what will we know? Well, we will know x bar, we will know s, and we will know n. So the T transformation, which looks similar to the Z transformation, we're still calculating the difference between the sample mean and the hypothesized mean, but now we're going to divide by s over the square root of n. Now the problem here is that T is not normally distributed. T is not normally distributed. So what we need here is the appropriate distribution for T. And until the very beginning of the 18th or the 20th century, we didn't really know that. But thanks to this gentleman, W.S. Gossett, we now do have a distribution for the t-test statistic, and it's called the T distribution. Sometimes it's called the student T or student's T distribution. And Gossett worked for Guinness Brewery, as a matter of fact, and Guinness, back in when he was working there, had a policy against employees publishing or sharing any kind of trade secrets or anything like that. And so Gossett didn't want to actually publish, but he was talked into it by, I believe it was Pearson. And because this idea that he came up with of degrees of freedom and the correct t-distribution was so important. Now let's talk about that for a second, okay? T-distribution is defined as, all right, let me say it this way, the t-distribution has only one parameter. And that parameter is called, let's see, only one parameter. And just as a reminder here, how many parameters does Z have? The Z-test statistic has 2 parameters. Mu, which is 0, sigma, which is 1. Okay, and those are the parameters for the model. But T only has one parameter, and it's called degrees of freedom, and it's defined to be n minus 1. The other thing that I want to bring up here is what we call S over the square root of n. I like to call it the adjusted standard deviation, but that's not really its name. The name that statisticians use is the standard error, or the standard error of the mean. That's the technical name for the sample standard deviation divided by the square root of n. So what is the deal with this t-distribution? Well, there is only one standard normal distribution, which is the n01 distribution. But there are many different t-distributions. All of these distributions have some things in common, though. One of them is this axis of symmetry that passes through 0. So the t and the z distribution are centered on 0, which makes sense because the t transformation has x bar minus mu, just like z does. So if x bar were to equal mu, then t would equal 0. So that makes sense that all of these distributions are centered on 0. So this n01 is the standard normal, okay, for the z distribution. And what these other curves are representing are the different t distribution curves. So notice right here we have the T3. Now notationally, the notation for the t distribution is t parentheses degree of freedom. And that's the notation we use. So the T3, so T3, that t distribution implies that n is equal to 4 because the degrees of freedom is n minus 1. So if degrees of freedom are 3, of course, n is 4. Okay, so the degrees of freedom are always 1 less than the sample size. So here's the key thing to see here. Okay, I'm going to go in and draw some sketches, or attempt to. So here's my number line, and this number line that I just drew is going to represent z values or t values. So let's start off by drawing, I'll try to sketch a reasonable looking standard normal curve, okay? So this is meant to be the z distribution, centered at 0. Now I'm going to make an exaggerated t distribution. So what happens with the t distribution, okay, is it's going to be more flattened out. Remember, both of these are density curves, so the total area under both of these curves is always going to be 1 in both cases. But the thing I want to point out here is that the t curve, okay, so say this is t with some degrees of freedom, whatever they may be, the t curve has a fatter tail than the z curve. And that's important when you start thinking about area. because if you pick a particular value on this axis, call it T star, say, or Z star, okay? And again, I'm representing this as the T or Z axis, or Z or T axis. What you have to see here is that the area under Z is less than the area under T. So there's extra area here. What that means is p-values, for example, are larger, oops, let me see if I can write this, are larger under T than Z. Okay, and that's important because remember, alpha is the significance level, and we're going to reject when p is less than alpha. So if we have a distribution that's producing larger p-values, it's going to take a more extreme data value to trigger rejection, okay, at the same alpha. Because to get, say that, let's just say that this p-value under the Z distribution perhaps is, say, something like, let's call it like 0.001, okay? The area under the T curve is going to be larger. So the p-value, if we were going to calculate under that curve, is going to be greater than the p-value under the Z curve. So if we want to have the same level of significance for T, we have to have a T value that's shifted to the right. The other thing to see about these curves is that as the sample size increases, okay, so here's the sample size is 4, here the sample size is 16, the T curve gets closer to the Z curve. As a matter of fact, we say T approaches Z as the sample size increases. So at n equal 30, both distributions give about the same areas. Now that's one of the reasons that that the threshold of sample sizes of 30 are used, because at 30 it won't really matter too much whether we use a Z distribution or a T distribution. Beyond that point, we would end up with the same probability values. Okay, so let's take a look at an example. Okay, one of the things that from here on out, one of the things that we're going to have to do is pay attention to the information that's given and see if that information fits with the assumptions that we're going to have to make. So in this example, a soil scientist is interested in studying pH level in soil for a certain field. In particular, she's going to examine a random sample of soil samples and measure their pH levels to assess if the mean field pH level is neutral versus the alternative that the mean pH level is acidic. And we're told alpha is going to be 5% here, okay? So what is the null and alternative hypothesis? Well, the null here is going to be that the mean pH is equal to 7, and the alternate is going to be that the mean pH is less than 7. So that would be the correct null and alternative hypothesis. Now, suppose it's reasonable to assume that the pH levels of all the possible soil samples that might be drawn are normally distributed. The scientist takes 5 randomly selected samples of soil from the field and measures the pH level. And here's the data. So what do we have here? Well, we've got a small sample, okay? We have a small sample, and sigma is unknown. Sigma is not given in this example. Therefore, we're going to use the T distribution, or what's called a t-test on the TI calculator. So let me get my calculator going here. Okay. And what I'm going to do, first thing we're going to do is enter the data, okay? And let's see, I'm going to go to Stat here and Edit. And I'm just going to use, I think I'll just use L1. So I'll clear what's out of L1. And I'm going to enter these data values. So we got 5.8, 6.3, whoops, let's see, how about 6.3, 6.9, 6.2, and 5.5. So there's the data. Now, when we go under the Stat menu and over to Test, notice choice number 2 here is T-Test. So I'm going to choose number 2. Now, just like the Z-Test, there's an option to enter stats. There's also an option to use data. So I'm going to switch over here to data. And what that's going to allow me to do is just enter a list instead of entering the sample mean, standard deviation, and so forth. The calculator can actually go into the list and calculate that. So this is a bit of a time saver. Now the hypothesized mean is 7, the data's in L1, frequency is 1, the direction of extreme is one-sided to the left because the theory is that the field is acidic, so we're expecting the average pH to be less than 7. Now we'll calculate. Now notice what's printed out. The t-statistic is calculated for us. The p-value is calculated for us. The sample mean is given. Sample standard deviation, sample size. So all of the information that we're going to need for many of the problems is going to be printed out using a t-test. So really, when you're doing your homework and when you're doing problems in this class, I'd say if the problem fits the assumption for a t-test, don't worry about the order and what you're being asked to do in terms of the order of the subparts of the problem. Just put all the data or put the statistics into the t-test and do the t-test. Because, for example, in this problem, okay, when I go and look at the next part of the problem, we're asked to find the observed sample mean pH and the observed sample standard deviation. Well, notice that those two statistics, 6.14 and about 0.53, now can I remember, is that X bar? I should have written it down, huh? S equals, I think I said about 0.53 approximately. So again, though, those are both coming off of the t-test on the calculator. Corresponding p-value. What was the p-value? I don't remember. Let's see. About 1%. It's just about 1%. So p-value is approximately, I'd say, about 0.01. And since alpha is 5% here, 0.01 is certainly less than 0.05, which means the p-value is less than alpha, which means we should reject the null hypothesis here. So we found statistically significant. So the answer is yes, the data are statistically significant. And we're asked to give an explanation here. And I would say one way we could say that, explain this, is because the data were unusual enough given the assumption that the fields, or let's just say the soils, pH, our average pH, was neutral. We have found statistically significant evidence that the soil's pH is acidic. Okay, so that's that. That's the end of that lecture. So part 3 is next. Stay tuned for part 3.